Hi guys, so it's our third class, and today we will be doing fluid simulations of involving the temperature, density, and particles. And that's what we're gonna end up with. It's actually the same simulation, just with three different variations of the fluid emitter. So it probably could be described as a fireball, but the same technique could be applied for the missile trails, for any fluid emitter that travels through the 3D space, leaving behind the trail. And with this particular example that we will be recreating today, we will be looking for a solution to make the smoke or density to extend in omnidirectional fashion away from a path the emitter travels, which is quite problematic using default Maya settings. So let's get back to Maya, and here's the file that I downloaded from web, and it's made by one of the Autodesk developers, Duncan, and it's illustrating similar technique, and we could start our discussion with this file. So it consists of this 3D container and one fluid emitter, and there's a NURB sphere which does not participate in the simulation. So we're practically dealing only with the container itself and the emitter, and the emitter set to be as a omni with minimum and maximum distance set to 0, 1. That means that the density will be, or temperature and the density will be emitted from the center of the emitter, and the distance from, or radius, specified by the max distance attribute. Other than that, it's all default settings and such. So if we would simulate this and render, we would end up with this particular motion. And what we see here is that even while there is a temperature involved, and it tries to extend or make the fluid move in multiple direction, in an omnidirectional fashion, it's really not happening well. So let's go back to Maya. And start new scene. Dynamics module, fluid effects, create 3D container with emitter. And just to make sure that we're working using the same settings, I use edit reset settings and hit apply. And here's my container with a default omni emitter. So if I would change the omni emitter to volume, and let's, under the volume emitter attribute, I change to sphere, and I also change the fluid drop off to 0, meaning the whatever is being emitted from the emitter does not is emitted equally from the center to the edge to the boundaries of the emitter. If the fluid drop-off would be anything other than 0, then there will be less emission as distance between the center of the emitter increases. Okay, so if I change the end frame of simulation to 400 and playback, we will be able to see that it's emitted default density. So I go to fluid shape attribute, and under lightning select self shadows. I deselect keep voxel square, and instead I type 50 by 50 by 50. To set up the resolution, I change temperature to dynamic grid because I'm interested in emitting the temperature into the fluid container, and I go to dynamic simulation, set gravity to 0, and high detail solve to all grids, which is a good choice if you're looking to create accurate simulation. And under display, I choose boundary draw to bounding box and wireframe display for the particles off, meaning there are no particles. If I switch to wire view, the particles will be not displayed that represent the density of the fluid emitter. Then I go to content details and check what my density values are, and let's just set buoyancy to 0. It actually would make no difference since we already zero the gravity, and as I already mentioned that in a previous classes, is that the density buoyancy is a simple multiplier to the gravity. They work in unison together. And under the temperature, I set temperature buoyancy to 0 as well. The temperature buoyancy does not work with the built-in gravity attribute, so it's independent all on its own. And select emitter just to make sure that we're emitting the temperature, which is called heat emission. And if I start to play back in shaded view, we would be able to see that the both temperature and the density is emitted. I can always go to fluid attribute, shape node, and under display, turn shaded viewport as a temperature display. As soon as I select the temperature display, all we see in the OpenGL viewport is temperature representation of the. I rewind simulation to the first frame and play back. So what we see right now, even while it's being displayed as a white substance or volume, is actually a temperature. And it doesn't matter how long I will be playing back this simulation, it will not move. And the reason why it's not moving is because the buoyancy for the temperature is set to 0. We did that just a few minutes ago. The only way to make temperature move is to use a buoyancy attribute. The positive attribute will move buoyancy along positive y-axis. Let's observe that. Let's put 10 here, for example, so we can see result quicker. So we can see that happening. And if I put negative, it will apparently move it in opposite direction, which is down. Negative along y-axis. Alright, so that's clear. But in the real world situations, the temperature represents hot air, or the air with the higher temperature relative to environment. And from what I know from real world experience is that high temperature tend to move toward cold temperature, meaning if we would have a hot bowl of hot, or the bowl of hot volume or temperature like this, it would be extending in every direction from its center, and apparently it's not happening. It doesn't matter how much I put scale of the temperature, I can change all the settings here, they will not make this temperature move. The way it's being kind of cheated is using a temperature turbulence attribute, which would produce some kind of random velocity vectors. Let's display velocity by clicking velocity draw, and let's draw length. So you can see that as soon as I change the turbulence value for the temperature, there are velocity, like a noise velocity values generated by simulation. And that's exactly what we see in this example, is that the emitter travels through 3D space. It emits temperature, there's no gravity, no other forces that affect the fluid simulation. The only reason why the fluid is moving here is because of this turbulence value set to be not 0 for the temperature. If that temperature value would be 0, this simulation would look very boring, meaning all we will able to see is just a red line left by the trail. There will be no motion happening there. But this approach is not really very accurate, because we're dealing here with with the random velocity vectors generations, and they tend to work in a very brutal fashion, meaning like they don't take into account the value of the voxels, meaning they displace in 3D space both low density voxels value and high density, and that results to simulation with a lot of artifacts. And if I would make the simulation run long enough, like this for example here, then this velocity noise produced by turbulence will keep going, and we already start to see the artifacts like a digital pattern here, like evident especially at the area that was emitted earlier during the simulation. So somewhere here where the temperature just was emitted recently, the noise is not yet evident, but here it's already taken a shape, and if I run the simulation for another 2 seconds, then all of this area here will be looking like one massive noise generated pattern. And for the missile trail simulations, that could be quite an issue, because in most of the trails, smoke trails, we would like to keep the trail left where it is and yet evolving properly. So back to this simulation here, let's zero turbulence off, and as a matter of fact, let's just turn off the temperature simulation by going to content method and choosing temperature off. And all we're left with is a dynamic grid for the density and dynamic grid for the velocity, meaning the only two grids that we will be simulating is a density and a velocity. Even while the emitter set to emit temperature, that emission will be ignored and not taken into account. Under Display tab, switch from temperature as render. You can switch to density. It will be exactly the same thing, because the density and as a render without the temperature is practically a representation of the same grid simulation. So if I play back it now, we would be able to see the same happening with the density, because there is no field or no force affecting the density. And what interesting with the fluid is that it does not matter really whether the voxel has got a density or any value stored in it or not. And once again, if we change to wire view, I can see numeric representation of the density by switching to numeric field, and we see here that each voxel show that it's got some density value set to it. But even while the voxel's got density value specified, nothing is happening, and that's because there's no motion yet. So in order for the fluid solver or for fluid algorithm to start doing its work, it needs something to trigger the simulation, and that something is usually a motion or velocity. And that brings us to the discussion about how do we inject that velocity into the fluid container. We're given first option is the built-in gravity field. That attribute here under dynamic simulation gravity, even while it's being placed like outside of the density and the temperature area. So as you can see that the density and the temperature has got dedicated set of the attributes, and dynamic simulation area here is kind of resides above those separate areas dedicated to specific grids such as the density, velocity, turbulence, and temperature. And we're supposed to assume that dynamic simulation area of the attribute editor deals with the attributes that shared among each grid, among density, among velocity, turbulence, temperature, and fuel. And it is true in terms of the viscosity attribute, friction, damp, and such, or the solver, substeps, start frame, and such. But it turns to be that the gravity attribute, even while it was placed in this generic area, only works with the density. So, by other words, this gravity attribute could be easily relocated under the density area here. Or what would make sense is to get rid of it completely and just leave density with the buoyancy. So every time we need a buoyancy for the density or gravity for the density, we change it here. Instead, we're given two sets of numbers, buoyancy and the gravity, both of each multiplied against each other. So we could use gravity, which given to us in two numbers, to have things, to keep things simple. We could always keep the buoyancy as 1, because 1 is a good multiplier number, and then changing the gravity positive along positive y-axis, minus negative number would move density in a negative direction. And if we start to playing back the simulation, that we would see as as soon as the fluid start moving, it's already starting to produce some kind of shapes to it, and those shapes much more elegant than the ones that being created by the temperature turbulence velocity. And that's because what we see right now is a, let's say, pure fluid simulation, meaning it's as accurate as it could be by today's standards. And if the goal usually, I, for example, set to myself, is to not to interfere with this simulation much, but only affect it only when I need to. So apparently the biggest challenge is to make the density, or the smoke, let's call it smoke for this example, is to start introducing details as soon as possible, and as with much details as I possibly could get from it from the beginning, with the highest resolution possible. And in order to do that, we're given not that many choices. One of the choice that is pretty good and quite used often, it could be found under the emitter attribute, and it's so-called fluid emission turbulence. And what this turbulence does, it does not generate the velocity turbulence. It generates a density or emission of the density. It affects the pattern of the emission. So let's switch to fluid shape tab and change the gravity to 0. So if I play back the simulation, nothing would happen. And now I go back to the fluid attributes, fluid emitter attribute, and I change the turbulence to 1. And let's see how that affects and I change turbulence speed to 0, so it's not changing. And I start playback, and as we can see, nothing seems to be yet. So let's increase the turbulence, and we could say that increasing the turbulence number, we increasing the contrast of the turbulence. So it's more evident whatever is happening here. So we can see that instead of being emitted in a perfect sphere, we're now given some form of pattern to it, or the density has been eaten away. And once again, there is no velocity. There was no velocity emitted into the fluid. All we did is just broke down the emission of the density. So if we would introduce gravity again, then this pattern, that imperfection of the found inside of the emitter, would affect the way the fluid moves. And we already start to see is that we see that it's already not, it's moving already in much more interesting fashion comparing to the motion that was initiated by the emitter that was a solid ball. So now let's zero gravity back and return to the emitter and change turbulence frequency from 1 to 0.5, and let's see what that makes, what difference that makes. And what it does, it kind of scales up the let's say 3D texture of that turbulence. If I make number larger, it make it more frequent. You're able to see it here. Like if I make it even larger than that, then the features will become smaller and smaller, and you will get to the point when you're not able to see the noise at all, because the features of the individual noise is that small. And apparently turbulence speed would affect how fast the pattern is changing over time. Value of 0 that we were using showed no changes, meaning it was a static locked emission. Okay, so that's clear, I hope. So now with that in mind, let's back to the gravity, increase it to 10 and playback. You know what, let's, instead of having a square container, let's change it, change its height to 20. And since I don't want to like make computer slow to respond here, so I'm gonna lower resolution of the simulation from multiplier of, let's say, 3. So it will be 60 along y-axis, and it would be 30 along other axis. So it's the same multiplier here. And I started playback, and we see that things moving in more interesting fashion. Still quite boring. Another attribute that I would be changing a lot is simulation rate scale. My preferred number is number 3, and that already I mentioned something that makes things happen much more interesting. So what we have here is that we have a fluid simulation running with the minimum or not yet introduced artifacts, meaning if we would run this simulation for a while, it will deliver us quite a good. I'm changing the boundary of the fluid container to be only the floor or negative y-axis will be closed, all other walls will be open. So if I will keep this simulation running, you would be able to see that there will be no artifacts introduced. It will be clean, nice simulation. And now another attribute that we would like to learn and be comfortable with is a swirl. Swirl is quite a common attribute. It can be found probably in every fluid solver in multiple applications. And what it does, it finds an areas where the velocity builds up some kind of curvature. Unfortunately, we're not really able to see it's displaying here. Kind of, you know, if we would take a look there, there's some areas that is being considered as the potential candidates for the swirl to happen. And that number here, we're able to find, or let's say by changing number, anything from not being a 0, let's say let's put 1. 10 usually is like as high as you can get. And if I change this number here, what we do, we kind of enhance the motion of the we kind of, you know, trigger all of those additional swirls. It's still quite delicate weight to deal with fluid velocity. It does affect what fluid container would do without the swirl, but most of the time, if used properly without abuse, it will give quite a good result. And I was even able to map those attributes like a swirl. I could apply texture to it, and not that quite oftenly used trick, but it could be quite possibly done, that you would apply let's say a ramp that you would make a swirl more at the bottom of the container and less at the top, and that's something sometimes desirable too. All right, so let's finish this theoretical conversation about the fluids. And what I'm saying right now, I think, is quite important for anyone who wants to learn fluids and be efficient with them. I'm not covering the attributes that rarely used, and those aspects that I just mentioned are the ones that I keep in mind constantly while working with the fluids. Okay, so now let's return back to gravity. With zero gravity down, we rewind to the beginning. I hit play, nothing happens, and you already notice that the gravity is given to us as a one single number. It does not have a direction here, meaning like it's either up and down. The only way to affect the gravity direction is to tilt container in a way pointing the y-axis in the direction that you would like things to happen. And that's probably fine in some scenarios, but I prefer to have a deeper control over that, and for that I would use a field gravity. So if I would select container and go to field and choose gravity, then this particular node that is placed in outliner here, and it's also could be found in OpenGL viewport here, it doesn't matter where I place it. It's got its own attribute editor, as you know, and as you see, instead of just one number that controls the magnitude of the gravity, we're given attenuation, we're given all three directions here. We can specify max distance, fell off curve. All of this beautiful stuff is actually could be used in advantage for while working in a simulation. And if I select this container here and I duplicate it, unfortunately I would have to kind of duplicate. Let's parent the emitter under the fluids like this. So you can select emitter and then select fluid and hit P key for the parent, or you just click and drop it on a fluid node. So you can select this container here. Let's delete gravity for now. So we have a fluid container and emitter. That's it, nothing else. If I go to Windows, relationship editors and a dynamic relationship here, I can see, and with the fluid container selected, I select emitters and I see that they are connected. Okay, so if I duplicated this by using added duplicate, I will have to recreate the connection again, meaning like I would need to connect both of them together. My preferred way to do, I just copy, Control C and Control V, and as you can see, when I pasted this, whatever was copied, it just like importing this same scene back into this particular scene. A very convenient way to, but it groups everything, whatever has been passed it. So ungroup it. So what we have now is two containers right here, container 1, container 2, both copies of each other. So if I rewind to the beginning and start to play back, we would be able to compare both of them at the same time. As you can see, both exact replica of each other. So now select container number 1 on the left and put the gravity 10 for this guy, right? Now, so this container here on the left is being moved by the gravity that built into the container. Container on the right, we select fields and create gravity. Go to gravity attribute editor, magnitude to 10, so we got exactly the same. Direction to, I believe we should to put in +1, and everything else is by default, right? So there's no attenuation, direction and +y. Okay, we play back, and look what happens. It's exactly same simulation. There's no really difference, practically, no difference. And I'm sure if there is a difference, it's probably just a scaling factor or something, translation. And what we can see clearly here is that both fluids moving in quite nice fashion, meaning like it's something that we would imagine fluid would do, right? There are turbulences that not as a result of noise function, but the result of the fluid solver working. So now let's delete the gravity field. And instead of the gravity field, no, let's not delete, undo gravity field delete. And let's display velocity draw for those containers, okay? And velocity skip set to 2, and this one is to 2. So if I rewind to the beginning of the simulation, next frame, as you can see, there is no, on the first frame, second, third, you can see that as I advance through the time frame, even while there is a force that affects the fluid, only the voxels with a lot of density is actually showing us that they have some kind of value to it. So meaning like these voxels with a lot of density has got velocity already introduced, but the voxels here on the top of the container where there's no density, this remains to be empty. And if I will advance through the simulation, you can see that the velocity is practically the large value velocity vectors only happens where there's a lot of velocity. I mean, where there's a lot of density. It leaves those voxels practically intact, meaning like it's not affected by the velocity at all. Like there's nothing happening in the empty voxels. And that happens in the behavior with the built-in gravity field, and it happens if you select effect, field gravity. Okay, so in other words, what actually happens under the hood is that the magnitude of the field, and from class number 1 we know that magnitude is acceleration, right? Not that it really makes a huge difference in right now in understanding what the fluid is, but the magnitude is also a very good thing to know, that instead of just a word magnitude, we know that it's acceleration. All right. So what is actually happening here is that the magnitude value of the field of the gravity is being multiplied against the value of the density stored in the voxel. So if the voxel value of density value of the voxel is 0, then multiplying it by the field value magnitude, we're given 0. So that's why there is no velocity in empty voxels. If the velocity, if the density within the voxel is larger than 0, then we could imagine what happens. Number 1 will be equal to the voxel with the density value of 2 would receive twice as much force from the field, and that, while yet sounds quite unimportant, that what makes accurate simulation possible, and beautiful simulation possible too as well. Now let's delete the gravity field applied to this right container, and instead of the gravity field, let's select uniform field, and in the uniform field we say magnitude 10, right? Attenuation to 0, direction 0 in x, positive y, 0 in z. And let's see how that field affects and what happens, what the difference, right? So what is actually happening is that as soon as I hit play, every single voxel in a fluid container is being affected by the field. So every voxel, regardless of the value stored in it. And what happens now is that the fluid or density will be displaced in very brutal, forceful fashion, meaning like it practically just moves through 3D space. while simulation on the left that is being driven by the very friendly to the fluid gravity force that does multiply itself against the density value stored in the voxel, producing a nice looking simulation. The uniform field does not care about the density. It just goes ahead and forcefully displaces everything on its own way. And now let's just see what we have as a result. So result is quite evident, is that the simulation on the right looks very boring and ordinary, and it's very hard to get any good result from field like this. So now go to field menu, and from all of these fields, volume, curve, volume axis, vortex, uniform, and such, right? All of these fields could be used with the fluids. There's no really limitations, but only gravity field and Newton field will act in the same way as a built-in gravity field found in a fluid attribute editor, meaning only those two fields will be giving you accurate fluid simulation. All others, drag and such, vortex, uniform, volume axis, volume curve, they all will give you this type of stuff. And this is the last thing I wanna happen to fluid container. Is like, before the simulation even started, before you did anything, you already end up with something like that does not belong to the fluid container. Those velocity vectors are just like a mathematical formula that acts behind of the fluid solver. So if not so what we have here is like, when I play back simulation driven by the uniform field, we do see there's still some little motion here and there. The fluid solver tries its best to contribute to this motion somehow, do something, but its best efforts all lost in that impact that the uniform field does to it. And once again, all of these fields are, except Newton and gravity, will act this way. So for me, I, for example, made a long time ago decision of not using any of those fields again, only when I have to. And I left myself practically in 95% of the time only with the gravity and Newton field. Gravity field, while being quite limited, gives you still a lot of options. Let's delete uniform field, select the fluid container, Newton field, see the attribute editor. So we already were here, so I'm not going to repeat myself. Even while there seems to be not a lot attributes, it's still quite a powerful tool. One thing to remember that for sure that you can specify a volume to the gravity field, this thing here, and when you specify a volume, you can work with kind of limited area. For example, you can say that this field only will be working like in this particular volume that defined by the icon, and you can move it around and position whatever you want, or you can multiple of them and such. Rotating of the gravity will not produce any difference to the simulation. For changing the direction of the gravity, you would need to modify its direction that is being found under the direction attribute of the sorry, I'm dealing with the Newton field here, that we find under the gravity field attribute, direction attributes here. So this is the thing that we would like to affect every time we would like to change the direction of the where the gravity field is being pushed. The Newton field itself is even simpler than the gravity. It either pushes or attracts toward itself. That's it. It's also can be given a volume shape, and that's not seems to be not a lot, but most of the time you would be able to achieve a lot with these things. And yet, you know, we get from time to time we get to the situation like this, where we would like to, here with the simulation with the emitter traveling in 3D space, gravity force is not working here because gravity force is acting in one single direction. It's not omnidirectional. Newton field seems to be could work, but then you would need to position a Newton field along the path and then somehow animate that. And yet again, the Newton field will be acting in every direction. What we would like to do is to move introduce the velocity vectors along the surface. And for this example, let's go to File, New Scene. Let's say create a NURBS primitive, and let's select a cylinder here. Let's rotate the cylinder 90 degrees so it's kind of parallel to the ground, and we go to make spans, let's say 24. No, that's a lot. Yeah, why not? No, 12 would be fine. 16 sections, and scale it. It doesn't have to be any precise. I just would like to show you an example. So we have this guy here, and what I would like to do is just a piece of geometry. Seems to be like not a lot to it, and we apparently can display control points. So dealing with the geometry, the reason I brought the geometry into this conversation is to illustrate that many times working in applications like Maya or others, there are some dynamic artists who see the geometry as a great source to create your own custom fields. So, the situations when you run out of the tools. So let's say if in my particular case, as some individual who only works with two fields so far, gravity and Newton, I would like to be able to create my own field from time to time, and let's say, and I would like that field to be as accurate as a gravity and Newton field. By saying accurate, I mean it would be multiply its magnitude against the density stored in a voxel. And for example, if I take this piece of geometry and let's say I apply some form of deformer to it, create deformer, and I say nonlinear bend, and I hit T, and like this. So making a field like in this particular shape is definitely would be difficult of not using the like from a field menu, not using the geometry. So let's say if I have this piece of geometry, what I can do here, I know I have a control points, so I can say display or show control points, NURBS, show geometry, NURBS CVs, and I can I know that NURBS also has got surface points like this, and each of them has got its certain data associated with that. It's right here on the top of my tab. It's every time I move this point around, you see that the UV values change. So there are certain type of data that geometry can give to us. And in very primitive form, what I would like to show here is that what we can do is that we can, for example, create emit particles from this piece of geometry. So let's go to dynamics. It can be n particles, it can be just regular. Create particle, emit from object, right? And I say surface, and I say okay, so speed, and I set speed to 0, so I don't want the particles to move, and I set normal speed to 0 as well, right? And I say apply, and right now particles are not visible because we're on the first frame, next frame, and I can see the particles are right there, so there are particles generated, okay? And what is actually happening here is that this particle has got no idea about the surface is being emitted from, right? So if I open the outliner and go to the emitter, and I open the attribute editor for the emitter, I can say need parent UVs. You see this checkbox, need parent UVs. This option will instruct that the particle at the moment of its birth will be given some, let's hide this deformer, and let's hide the control points, display, NURBS, CVS, okay. So these particles will be given some piece of information about the geometry that is being emitted from, right? So let's go to emitter and change the emission rate to 10,000. So we have more particles emitted on the first frame, so that's how many particles we have. So now select the particle, open the attribute editor, and under the attribute editor, click general and go to the per particle and say no, go to particle tab and select goal U add, goal V add, and then select parent U add, parent V add. Okay, so now we got 4 more attributes. So what's interesting is that when we went to emitter and said need parent UVs, what that thing did is that it let every particle know its own parent. If we would specify parent U and if we would give particle an attribute parent V and parent U, then this attribute parent U and parent V will be storing information about where along U and V this particle was emitted from. So let's change the particle shape to spheres, current type, insert some down. Oh, you know what? We can also display the numeric, right? So numeric, and current type right now is default to particle ID. Let's go to max count and say max count of the particles we would like to see is 10. Okay, the beginning, next. So we got only 10 particles displayed. The way we deal with the max count attribute was covered in the previous class. Okay, so we got this, right? And right now we're displaying the particles ID, I believe, right? So, but instead of the particles ID, we can say right click on the parent V, create expression, and you can always copy and paste if you don't know what attribute name. So you do that in parent V, and now you see what happened in here is that every particle shows us it's a U and V value, or if right now we're showing parent V. Parent, in a term parent, is used to illustrate the geometry that was used to emit this particular particle. Okay, so we select this guy here, and this shows us that this particle sits on a V value of this NURBS surface is equal to 11. So if I right click and say surface point, and I click and kind of try to reposition this display. Is kind of hard to do with the low resolution. So it shows me that the value of V is 11.5, and that's somewhere like I need to be precisely place this marker where the particle is. But you got the idea, is that these particles, just because we selected under emitter, need parent UVs checkbox, each particles were given a certain piece of information about the geometry that was used to emit it. And in terms of the particle attribute naming, parent referring to source geometry. It's easy to remember. Okay, so now if we say goal V and goal V, okay, so goal V and goal U attributes only meaning something when particle is given a goal. So what we can see, we can select the particle, we can select the geometry, and we go to the particles and say goal. Okay, select whatever is here, reset settings, and say apply, close. So now you will select the particles and go to shape, find the goal, weight, and object area right here. Goal smoothness is how long the particle kind of takes to settle down. That's an entire new topic about the goals, but right now I would say that the goal smoothness of 0 makes particles stick to the surface immediately. So goal subject in a particle world means like you select the particle, you select the object or another particle, and you can stick that particle to the goal object, or like the object that will attract the particle. And the smoothness specifies how long the particle will try to live on its own before it loses any ability to move independently. Okay, and this attribute second one is kind of weight. It's like how much influence it's got. Value of 1, full influence. Okay, so now if I hit playback, if I hit playback, all my particles gathered in the same place, 0, 0 of U and V right here. So all the particles attracted to the U and V. So in order to make this particle stick to the same place where it was emitted, I can use its attribute parent V and parent U that was given since we choose need parent UV attribute, right? So it is very simple expression. You only learn it once and you would doesn't have to do it again. So what you do here is the parent V, you say parent V, you copy this. No, let's do this. You just say goal V is equal to parent V, and for the syntax I omit the name of the particles because Maya will fill it automatically. And for the goal U, I do the same thing, and I say U here and U here. Okay, so and I say edit, close. Okay, so rewind to the beginning, next frame, and you can see our particles emitted, right? Next frame, next frame, next frame. Now particle is moving because they already gold or stuck in the place that we specified with this expression, and this expression is telling it that stick to that area of the surface from where you were emitted. The reason I actually brought this into the conversation is that we have a geometry element here, and we have a particles. Particle is the dynamics. It belongs to the dynamics world. Geometry is not, and it's very easy to manipulate geometry versus the particles. But you can see how easily we can exchange the information between the geometry and the particles. So there is a bridge that we can define. Whatever we make to the particles right now, whatever attributes we define here in attribute editor, whether it's a per particle attribute or particle attribute, doesn't matter. Since the particle is dynamic element, we can link that particle into the fluid simulation. So we can take any information from geometry and transfer it to the particle, and from the particle to the fluid. It's only up to us to decide what piece of information we would like to transfer. Another beautiful thing about the goal object, goal particles, or the particles that were affected by the goal, is that now the particle knows much more about the object. So if at the time of the emission all we had is one option, is to need parent UVs, so the only thing we were able to give to the particles is the U and V value of the geometry that emitted it. We were not able to give any other piece of information. But when we make particle goal to the object, particle suddenly is able to get much more information. And to get that much more information, there are those buttons here, 5 buttons. Create goal weight pp, world position, world normal, world tangent, tangent v, right? So watch, is if I click this button here, it will add the attribute here. So it's kind of shortcut to create. So I hit all of them, right? I hit, and let's say deselect the particle, so attribute editor is refreshed. And you can see how many attributes we added. We added 5 new attributes. And those 5 new attributes is now reading information from this geometry. And what they read information about the normal, so each particle know what normal direction. If I select this NURB surface and I go to display NURBS normals, shaded view only, okay, like this. And I believe you go to the shape node and say NURB surface display, you can scale the size of the surface normals like this, like here. So you can see that's a NURBS normals. The same exists for the let's say edit delete by type history. It's strange that the normals of this UV is actually, I mean, of this NURBS object is not really 90 degrees to the surface, and that's probably because of the deformer, I believe. Maybe not. Yeah, it's kind of strange. What if I rebuild? Edit mesh, edit fluid. Need to go to surface and say edit NURBS, rebuild surfaces, and I say keep CVs. Cubic is fine. Apply, close. No, it doesn't want to. Okay, it doesn't matter. So we see that this NURB surface has got some normals already in a place, right? So I say display NURBS and I hide normals, okay? So, but these particles, they already know the normals of the surface because we gold those particles to it, and we press those 5 buttons here, and those 5 buttons instruct that each particle should know what normal direction of this particular point on a NURB surface is. It also knows U direction and V direction, and not just U and V direction in local NURBS space or polygon, but in the world. So let's say, let's go to the front view and hide everything, make background like white like this, and say create curve tool, say linear, and press X so you snap to the grid and draw a curve in form of arrow like this. And I will even go to the top view and make another arrow like this. So it's like this arrow made of the curve, okay? And if I hit W, the pivot point of this curve is here in the world origin. So I say display grid, and you can see that this arrow sits in the origin. So I display this guy here. The arrow seems to be a little large. What I would like to do is to create instance for each particles of this arrow, and I select those points here and make arrow slightly better looking, but you don't have to do it if you don't want to. Okay, so I have this arrow here like this. So what I can do now is that I can create instance for each particle. So I go to dynamics module and say particles instance, right? And I say apply, and boom, each of these arrows, each particle now receive an instance of the arrow. But now I can go to outliner, select particle, open attribute editor, go into instances tab, instances tab, where here, instance geometry, okay. And here under the under the aim direction, you can choose which rotation values you would like to specify, and you can say along normals, bam, and you can see what is actually happening is that this particle knows about the surface of the normal, so your instancer is now points to direction of the surface normal. But you also can change it to tangent v in the world coordinates, and now you can see that the arrows, or the particles really, points the arrow in the direction of v direction of the NURB surface. It could be polygon 2, or we can say along u. Okay, so you got the point. Now they all pointed. So if I, let's say, go to particles and let's, instead of max count of 100, let's say 1000. Okay, rewind back to the beginning, next, and instead of the particle displaying as a numeric point, and what happened in here is that we have tons of arrows all showing us direction of the data. It's a data. We visualize the data stored inside of each particles, and this particle data is stored in the particle attributes, and we know that any attribute stored within the particle can be used to control the motion of the fluid. So that finally brings us into the conversation about the example that we were looking at the beginning of the class in here. So what we did here, what we're gonna do here, is that we will create a particles, very simple particles, and we will emit particle from it. We will be dealing only, it's the same render, I just duplicated 3 times. You can see it's here just for kind of visualization purposes. We will animate the emitter traveling in a straight line, and then we will emit particles from this from a geometry here that sits in exactly the same place where the fluid emitter is, and those particles will leave the geometry, its parent, knowing, let's say, knowing normal direction of the geometry, which is in this particular case would be just the velocity. And then we will freeze those particles and practically will stop them moving, but we don't have to keep them moving because we can turn any attribute into the field, into the magnitude, into the force. So what misunderstanding is often happens among those who start working in fluid dynamics is that they think that if you need to emit some kind of force into the fluid container, you need something moving, like it's supposed to move in 3D space to be able to emit a velocity. So for example, if I new scene is a fluid create 3D container like this, right? And if I set this last frame to 400 and I play back this thing, nothing happens. So let's say if I say particle create emitter and I move this emitter here, and let's say if I play back it now and I want to particles to only be 1 particle, so max count to 1, and I set emitter from being volume, I would like it to be directional, and I would like it to move along x positive axis, right? So I do this, I play back, and I say that the speed is 1. Okay, so we can see that the particle is moving here, right? So what I can do now, let's say I would like to emit some kind of force into this fluid container, right? And I say, I select this fluid container and I set resolution to 30 by 30 by 30, and I say display velocity drop. But since there is no velocity yet inside of the container, nothing happening, right? So I can select this particle, and I can display this particle as a sphere so I can easily see it like this. And I select the fluid container, and I say fluid, add content, emit from object, okay? And I say okay, fine. And I say no density emission, I don't want a density, I don't want this, I don't want this. It's all 0. It strangely does not give me ability to emit velocities right from this dialog box. So in order to emit velocity, I would need to go to the emitter that I just would create for this particle here. And already here under speed method, I would say add or replace. Right, so inherit speed method, inherit velocity 1. So what I'm saying is that the particle velocity will be emitted into, or speed of this particle will be emitted or injected into this fluid container, right? So now I play back this thing, and hopefully, yes, we do see that the particle emits velocity into this container, okay? But what's actually happening here is that what most of the people do, they think if I need some kind of velocity inside of the fluid container, I would need something moving through this container, meaning like if I need velocity inside of the fluid container from left to right or from bottom to top, I need to get particle and move that particle from left to bottom, from right to left, and such, right? Replicating the motion that I would like be happening inside of the fluid container. But it is absolutely not necessarily, because particle can be sitting still. You can define any vector attribute that could be used to set a direction, such as like a velocity, and then turn that velocity into the force, into the field, because a force, the magnitude, is nothing but the direction, and the magnitude you just multiply it with a larger number. So that file that we see here, I already worked on, and I set it together here, and this class already taken a while. This is a good place to end for this week, and we will pick up the next week right where we left. As always, if you have any questions, please drop by the forums. Thanks for watching. It was fun.